Okay, hello everyone. Today I'm going to give a high-level introduction to zero-knowledge proofs and introduce basic about ZK SNARKs. Finally, I will introduce the current status of ZK SNARKs and how we choose ZK SNARKs candidates in use for our ZAND network. There will be several benchmark comparisons between different privacy-preserving approaches. In this talk, I won't discuss any zero-knowledge proof constructions. Please feel free to interrupt me if you have any question. So, nowadays, cryptography is widely used in building secure systems. However, most of these crypto primitives usually offer security for data. For example, encryption schemes provide confidentiality for data. Some people, Alice, can encrypt her secret message to Bob, and Bob can decrypt it if he knows the key. Cryptography also provides authenticity. For example, people can digitally sign some message to Bob, and Bob can authenticate the validity of the signer by verifying the signature. So, a question coming up is how do we offer security properties for computation? That is, how to hide secret information to other participants in computation. What if some participant behaves maliciously and not following the protocol description? What if some participant doesn't actually join the computation but keeps sending dummy messages? Cryptography proofs is mainly proposed to solve this problem. It is usually used to offer privacy-preserving property for computation, especially it allows people computing correctly and securely without revealing secret information of honest participants to malicious participants. Cryptographic proofs are usually used in protecting malicious behavior, especially in today's distributed protocols. Among all kinds of crypto proofs, zero-knowledge proofs is the most common and widely used one. It is extended from the research area called secure multi-party computation in 1980s. In high level, a secure multi-party computation protocol is a protocol run by M parties to jointly compute the function of their private inputs, but each participant doesn't reveal any information about their private inputs xi correspondingly. Finally, each honest participant will know the joint output y correctly, but it does not reveal any information about their secret information xi to malicious parties. After zero knowledge proof is proposed by the Turing Award winner Silver Mikali and Shafi Goldwasser, like in this picture. And after a long line of research, zero knowledge proof has become kind of independent of research area from secure multi-party computation. Before I introduce what is zero knowledge proofs, I would like to give in a story called the Alibaba Cave to give the intuition behind zero knowledge proofs. In this story, there are two people, Alice and Bob. Alice claims that she knows some secret word to open the magic door in a cave, but Bob does not trust him and would like Alice providing that she knows it. The most trivial way, of course, is to immediately telling the secret word of the magic door to Bob. However, Alice wants to keep it as a secret and does not want to let Bob know the information about secret word. So the question becomes, how does Alice can convince Bob that she knows the secret word to Bob, but without revealing any information about the secret word. Thus, the the solution to this problem is that they can do the following process. The first step is that both Alice and Bob come to the cave, and Alice enters the cave first. Note that there are two paths leading to the gates, and Alice can take either path 1 or path 2, but she doesn't allow Bob know which path she takes. Bob will wait until Alice goes in, and note that right now Bob has not come into the cave, so Alice doesn't let the Bob know which way she takes. And then Bob can enter the cave and randomly select an exit path 1 or 2. For example, in this case, if Bob selects path 1 and claim that Alice and tell Alice that she should exit from path 1. Since Alice knows the secret word, she can open the gate and exit through path 1. And if Bob chooses path 2, Alice can just exit through path 2 because she enters in path 2 to the magic gate. It is easy to see the fact that in this process, Bob does not know the secret word during this process because Bob doesn't enter into any path and go deep in the cave. Thus, this process is a cue for Alice if Bob is malicious and if Bob would like to know what is secret word. But here comes a problem. However, there's another question. If Alice doesn't know the secret word, she can still have chance to cheat Bob if she doesn't know the secret word. Why? Because if Alice does not know the secret word, she can still win with chance 1/2. Indeed, since Alice does not know the secret word, she can first guess which path Bob will claim and let her goes out from. Thus, she can convince Bob with probability 1/2 if if Alice can guess the path correctly. Even if Alice doesn't know the secret word. To solve this problem, Alice and Bob can repeat the whole process multiple times, let's say n times. This process repeat this process large enough times, and Bob admits that Alice really knows the secret word only if Alice exits from the correct path every time. Why they can solve the problem by repeating this process n times? If Alice knew the secret word, this case will be the same as they just do the process one time, because Alice can always exit through the path Bob claims correctly. This is easy to see, and Bob does not get any information about the secret word from Alice. The main difference is the case that when Alice does not know the secret word, if she doesn't know the secret word, Alice can successfully convince Bob only if she can always guess the path Bob will claim correctly every time. But this happens with probability 1/2 to the n, which is very small and negligible. Therefore, we say Bob is convinced finally with very high probability if they finish the whole process n times correctly. Thus, the whole process between Alice and Bob is actually a zero-knowledge proof protocol that Alice is proving he knows some secret to Bob, but without revealing any information about the secret word. And it is a zero-knowledge proof should satisfy the following three properties that we can conclude it from the example Alibaba cave. The first one is called completeness, which means that an honest verifier will accept the proof from honest prover. In such an example, it means if Alice really knows a secret word and behaves according to Bob's command, Bob will always be convinced about the fact that Alice really knows the secret word. The second property is called zero knowledge, which means the protocol is secure against to malicious verifier. That is, the prover does not reveal any information about his secrets. Recall that in the example, Alice does not reveal any information about the secret word to Bob. The third property is called proof knowledge, which means the protocol is secure even against to malicious prover. That is, the prover really knows her secrets and cannot cheat the verifier. In the Alibaba cave example, if Alice does not know the secret word but intends to cheat, she has to guess the exit path every time and wins with very small probability after repeating large enough times. Before 2010, most zero-knowledge proofs are just theoretical tools, and there's quite a few useful applications in practice. However, since the blockchain technology appeared in 2008, people find it is quite useful in protecting secret information in blockchain. Since blockchain can be viewed as a public ledger, any participant in the blockchain system can be a prover who takes input some public function description and his private input, and then he can generate some public value y and prove. He can post the public value y and proof on the blockchain, and every participant can see the proof and public value to verify the validity of the proof. Note that all these values, only the x is the secret value of the prover, and every other values are public and can be get by any verifier. That is to say, verifier doesn't need the secret word to verify the proof publicly. For example, the public function can be in the following form. It can be some money transfer function, which calculates the balance of Alice and Bob after the money transferred from Alice's account to Bob's account. The secret input of the function can be a string that including identities of Alice and Bob and the transaction amount in this money transfer. And the zero-knowledge proof is generated using the public function and some secret input of prover, and the prover is generate public value y and proof, and the verifier can verify this proof and using public value.